Hello everyone. We have another problem we're going to try to analyze using recursion trees, and we're just going to jump right into it. So first thing, identify the additional cost. Here the additional cost is cn squared, different than the previous problems we've seen. So we want to analyze this problem using a recursion tree. Analyze with recursion tree. So we need to know the cost of the first recursive call. Well, that's just the cost in the equation. That's cn squared. That then gets divided. My original problem gets divided into 3. I'm making 3 recursive calls. 3 recursive calls of size n over 3. So this gets split into 3 recursive calls, each of size n over 3. As we've done before, let's keep track of the size off to the side. The size at the first level is n. The size at the next level is n over 3. So we're going to plug that size into the additional cost. So we're plugging n over 3 into cn squared. So c times n over 3 squared, c times n over 3 squared, c times n over 3 squared. Each of those recursive calls will get split into 3 recursive calls. The size of the next level is taking the size of the previous one and dividing by 3. So size equals n over 9. So I'm going to plug n over 9 into my additional cost. So here I'm going to have c n over 9 squared, c n over 9 squared, c n over 9 squared. And I would have a whole bunch of copies of c n over 9 squared. Each of those 9 problems would get split into 3, and so on and so on. We need to compute the cost at each level. The cost at the base level here is cn squared. On the next level, I have 3 copies of c n over 3 squared. The next level, I have 9 copies of c n over 9 squared. Just counting the number of nodes I have. So, if I want to add up all of these, this is different because they vary with our levels. They're not the same. In all of the previous problems we've seen, the cost was fixed at each level. Here, the cost, let's do more simplification. We have cn squared, then we have 3cn over 3 squared. That can be written as 3cn squared over 9, which is cn squared over 3. For the next one, that's 9cn squared over 81, which is cn squared over 9. So, I'm going to create a little table here for myself to represent all of the things I need to know. So I know the size at level I is n over 3 to the I. I'm continually dividing by 3. The cost at level I, let's look at what we had. Well, we had cn squared over 3, and cn squared over 9. That looks a lot like cn squared over 3 to the I. We want to use the size at each level to compute the height. We can solve for the height by taking our expression there, n over 3 to the I. We're going to replace the I with an h and set it equal to the base case. Setting equal to the base case, which again is 1, gives us n over 3 to the h equals 1. We then solve that for h and get h equals log base 3 of n. So we're adding up cn squared over 3 to the I for every single level of the tree. So t of n is equal to the sum of the cost at each level of the tree, which is cn squared over 3 to the I. What are my values for I? Well, I starts at 0. Why? Well, if I look up at the cost of the base of the tree, that's cn squared. That seems to check out. And then it goes until the height of the tree, which shouldn't be k, sorry, it should be h for the height of the tree. And I know what h is. So let's analyze the summation. T of n is equal to, I'm going to factor out the cn squared. We have the sum from I equals 0 to h of 1 over 3 to the I. To analyze a summation like this, it's typically easiest to bound it. So let's bound this summation. This is less than or equal to cn squared times the sum from I equals 0 to infinity. Because it's a geometric series, we are going to bound it above by an infinite geometric series. Doing so, we have the sum from I equals 0 to infinity of a third to the I. This equals cn squared times 1 over 1 minus a third. Skipping a bit of arithmetic, that gets us that we have 3cn squared over 2. So, all of that says T of n is in big O of n squared. If we want to bound this below, we'll do that in a different color down here. Bounding it below, what we do is we replace the entire summation with the first term of the summation, which is just 1. So this part here in purple shows that T of n is in big omega of n squared. Those two things together, it being in big O of n squared and it being in big omega of n squared, is enough for me to conclude that, therefore, T of n is in theta of n squared. And that's it. The way that this problem was different is because we expressed it as a summation. The reason we had to express it as a summation is because the cost at each level was not fixed. I could have written in a different notation, so I'm going to do that off to the side here just to show us. We could have written T of n is equal to the cost at the first level, cn squared, plus the cost at the next level, which is cn squared over 3, plus cn squared over 9, plus cn squared over, the next one would be 27, plus, the problem here though is I don't necessarily have a great way to write down this last term, but it's going to be like cn squared over 3 to the h. So I will typically write this as a summation because this expression looks messy. So this one over here makes me sad. So I don't like doing it that way. But if you like to write it out that way, totally fine. I prefer the summation. That summation here, this summation is the sum from I equals 0 to h. That's always what we're doing of the cost at level I. There's no cleverness involved there. That is always the summation we're analyzing. So if you want, you can just memorize that formula there that I just boxed in. But I recommend remembering how we attack the problem instead.